All right, 5.3, linear programming in 2 dimensions, a geometric approach. So in this case, we're going to basically continue on with basically linear programming, or basically thinking about it in terms of the geometric approach, means just the X and Y. As you'll see in chapter 6, we're going to expand that to be not just in the 2-dimensional space. So first thing I want to review is, again, a problem that maybe is familiar. So manufacturing of a lightweight mountain tent makes a standard model and an expedition model. Each standard tent requires 1 labor hour from the cutting department and 3 labor hours from the assembly department. Right away, you should be seeing, oh, we have cutting and assembly. Probably gonna have constraints that deal with that. We're probably also gonna have to have decision variables like X and Y, right? So we'll probably make X the mountain tents, or the standard tents, and the Y variable, the expedition model. So each expedition tent requires 2 labor hours from the cutting department and 4 from labor hours from the assembly department. The maximum labor hours available per day in the cutting and assembly departments are 32 and 84 respectively. If the company makes a profit of $50 on each standard tent and $80 on each expedition tent, how many tents of each type should be manufactured each day to maximize the total daily profit? Assume that all tents can be sold. All right, so we're gonna have to build the decision variables, so we kind of have to figure that out. So hopefully you're seeing that in this case, when I was telling you a long time ago, I said decision variables, right? So we have decision variables. So in this case, I'm going to say X is the number of standard tents, right? In other words, that non-expedition tent, just the standard model. And then we have Y is going to be the number of expedition tents, right? That's our decision variables. Now, the next thing you're being asked is the objective function. If we're just going to go down this list, objective function. If you're this company, what's your objective? To maximize profit. So we're maximizing, right? But we also probably need to figure out what is the profit function. So if we go back, we can go back to the previous slide, or you can take, so if we go back to the previous slide, right? In this case, if the company makes a profit of $50 on each standard tent and $80 on each expedition tent, so that means profit's equal to 50 times X plus 80 times Y. That's your profit function, right? The number of standard tents you sell times the amount you make for each tent, plus the amount you make on each expedition tent times the number of expedition tents you make. We're probably also going to need constraints as well. We've already answered the optimal value, by the way. In this case, we're maximizing, okay? And now we're going to have problem constraints. Constraints. So problem constraints in this case are going to be basically that idea of the cutting department and the assembly department, because that's the maximum amount of hours we can work, right? So we might have the, I'm going to just say CD for cutting department, and SAD, for assembly department. So in this case, in the cutting department, we spend 1 hour for the standard tents and 2 hours for the expedition tent. And we have a maximum of 32 hours available, which means we have to work less than or equal to 32 hours in a week. And then in the assembly department, it takes 3 hours to assemble that standard tent, and it takes 4 hours to assemble that expedition tent. And we have less than or equal to 84 hours in the work week that we can use. This is basically most of what we need. There's one last piece, which is the non-negativity constraint. Because are you going to make any negative tents? Are you going to make negative tents? The answer is no. You're going to always make what? Positive tents. So X must be greater than or equal to 0, and Y must be greater than or equal to 0. So these are all things you've already seen before, but now we're introducing a little more terminology to encounter. So if we plotted this out, you should get a graph like I'm just going to minimize this a little bit. So we have an assembly capacity line. That's this 3x plus 4y equals 84. And we're going to shade below it, right? Because we're doing less than or equal to. We could pick a test point such as 0, 0. And 0 plus 0 is less than 84, so that would make sense. And then we're going to have a cutting capacity line, which is this x plus 2y less than or equal to 32. Excuse me. And so 0 plus 0 is less than or equal to 32. And so we shade down here. Now you might be noticing that basically we have these corner points. So I'm going to go back and zoom this in again. So we have basically our corner points. And then I'll make something called our profit equation. Right? So if I was going to go and just put those in, well, 0, 0, how much profit do we make there? So basically we go back to our profit equation of 50 times 0 plus 80 times 0. That gives us 0, right? That's this profit equation that we're using right here. That's obviously not a profit maximizing point. You guys would have probably told me that already, but just want to show you that's one of the corner points. So we have 0 and 16 is the next one. So that means 0x, so 50 times 0 plus 80 times 16, right? And 80 times 16, we get 1,280, okay? Let's go one, we gotta go a couple more. The other corner point that we have is 20 and 6, and we'll also have 28 and 0. So we have 50 times 20 plus 80 times 6. And what does that equal? You guys type that in your calculator, see what you get. And then we'll have 50 times 28 plus 80 times 0. And let's see what we get. I think you get 1440 for one of them and 1400, but let's just double check. 1480, sorry. And 50 times 28 and 1400. So if you were operating this company, this right here is your profit maximizing allocation. In other words, you're going to produce 20 standard tents, and you're going to produce 6 expedition tents. That's going to basically be your profit maximizing optimal solution. All right, so let's move it on. So one way you can visualize this, which is going to be nice when we start going chapter 6, is basically you can think of that profit line. So I'm going to go back. I'm going to sketch out this graph for you. It's going to be a real rough sketch just because I want to illustrate this quickly. So as you can see, I sketched the graph out here right quick. This is our X and our Y. Now, the profit function, P is equal to 50X plus 80Y. If you want, you can rearrange this and write this as a Y equals equation. So you can see the MX plus B form. So in this case, I'd move 50 over to the other side. So I'd have negative 50X plus P. Now, if I divide both by 80, right, that's how I can rearrange this. Now, you guys can agree that this is just a constant, right? And so in this case, we can think of Y is equal to negative 5/8 times X plus some constant. So in other words, if you think about negative 5/8, that would just be a line like this going outward. And where it last touches, right here, is the profit maximizing value. Now, if you were to look at the nice graphic that's here, all these dotted lines coming out, that is different values of P moving outward for it. Either way, that's basically how we'll use chapter 6 when we start doing the simplex method. Now, if we return back to a problem we've seen before, which was the boat problem, you guys should have that pretty fresh in your mind because you just did that in 5.2. So I think I have all that information up here, and hopefully you guys do too. So let's pull that up real quick. So again, just to reread the problem, basically a manufacturing plant makes basically 2-person boats and 4-person boats, and they're inflatable boats. And they have time requirements that need to be devoted from the assembly and the cutting department. So for a 2-person boat, it requires 0.9 labor hours for the cutting department and 0.8 in the assembly department. For a 4-person boat, it requires 1.8 hours in the cutting department and 1.2 hours in the assembly department. The departments each have 864 and 672 respective maximum amount of working hours in a week. So 864 for the cutting and 672 for the assembly. So let's just go out and do this. So we have to just do what our decision variables are. So X is the 2-person boats. And I probably should say number of, right? Because it's the number of 2-person boats that we have. And Y is the number of 4-person boats. So don't skimp on that, because that does help you cue you in on how you're thinking about these things. Okay, so we had our problem constraints from before, right? So one of our problem constraints is 0.9x plus 1.8y is less than or equal to 864. And the other one was 0.8 times x plus 1.2y is less than or equal to 672. So this was our cutting constraint, and this was our assembly. Right, so those are our constraints. We also have the non-negativity constraint, which just basically means you're not going to produce negative quantities of boats, which seems obvious, right? You can't do that. So we have that. Now what we need is an objective function, and I'm just going to abbreviate things. And in this case, you're probably what? I think profit maximizing, but let's just double check. It says at the very bottom, if I move this out of the way for us, it says the company makes a profit of $25 on each 2-person boat. So 25 times X plus $40 times Y is equal to your profit function, right? And usually you'd probably write this as max P equals 25X plus 40Y. And that is our profit maximizing function. So what we would need to do is then graph this and figure out what our optimal solution is. What we're having here is, I'm saying, just to kind of get you guys familiar with this, feel free to go ahead and put P set as 5,000, set it as 10,000, 15,000, 21,600. You'll see basically those shift basically that if you go back and think about the line I was trying to show you a second ago. Actually, here's what we can do. Let's open up Desmos real quick, and I'll show you that on the Desmos. So scroll up, we'll go to Desmos here. And so we have all of our lines in there, right? Okay, so now what I'm going to do is I'm going to put in that profit function, which was 25x plus 40y is equal to, and what are all the different values of P that we're going to have? 5,000, 10,000, 15,000, and 21,000. So 5,000. Oh, there's 5,000. Okay, let's bump it up to 10,000. Okay, so you see what's happening? Here, let's just do it this way. We'll do 5,000, and then we're just going to say times 2, because that's 10,000, right? So you can see basically how this is moving out. I'll do another one here. We'll do 25x plus 40y is equal to 10,000. Whoops, oh, forgot the 5 there by that 25. And we're going to put that other 0 in there. And you'll see it's moving outward. That's basically what the profit function is doing when we're having different values of profit. Yeah, so you see how this is just moving outward. And now 25x plus 40y is equal to 21,600. And my hunch, before I go there, is that it's probably going to hit at that point right there. Let's see if it does that. Oh, yeah, no brainer. It does, right? And I think that is that allocation of what we said previously when we graph this out. And I'll make this bigger so you guys can see it again. When we graph this out, that is that allocation of 480 and 240 from previously when we graphed out this problem. So if we were going to do the corner point solution, we put in those corner points that we knew before, and our corner points from before, if you remember correctly, Well, 0, 0 is one of them, but I'm not going to bother putting that one in because we know the profit for 0, 0 is 0, right? And then I'll have 480 and 240. And then finally, I'll have 840 and 0. And if I put those in for the profit function of 25x plus 40y, we'll get the profits associated with each of those values. So let's put those in real quick. So in other words, we do 25 times 0 plus 40 times 480. So 25 times 0 and 40 times 480. I get 19,200. I bet, by the way, this is going to be 21,600. Shouldn't be a shock to you, but 25 times 480 plus 40 times 240 equals, don't take my word for it, type it in your calculator, make sure you get the same answer, $21,600, right? And then here we put in 25 times 840, and I bet this is going to be shy of that, right? So 25 times 840, 21,000. And so that's where you can see that this is pretty close to the green line. If you go back to our Desmos graph right here, you'll see that basically that point right there is 480 and 240, which is our profit maximizing value. Pretty cool. So what does that mean? That means we should produce 480 two-person boats and 240 four-person boats to maximize profit. I think it's kind of cool. So hopefully you do too. All right, so kind of a procedure for going through these kind of problems, these basically word or story problems. Step one is introduce decision variables. In other words, decide how you want to solve this. So in this case, I said two-person boats, and I said Y was four-person boats. That was my decision variables. Step two is to summarize relevant material in a table form relating to columns to decision variables if possible. That's kind of what we did before. I think some of you guys might see how the constraints work, but if you don't, what we did before when we did the 5.2 problem, we built a table like this, and you can do this as well. This is really helpful if you're first getting your, first doing these problems and kind of trying to get the grasp of it. You can do that as well. Step three is determine the objective and write a linear objective function. That's basically our profit maximizing function right here. Right. Step four is to write the problem constraints using linear equations or inequalities. And step five, the non-negativity constraint. That's exactly what we did. So let's turn to some of these other questions we have. So let P equal X plus Y, graph the constant profit lines to the points 5, 5 and 10, 10. Place a straight edge along the line with a smaller profit and slide its direction increasing profit. So hopefully you guys see kind of similar to what we were doing before. This basically would be, depends on which variable is more valuable. So in this case, Y is more valuable for you to produce than maybe X, because you get $10 for every Y value, every Y unit you sell, and only $1 for every X unit you sell. Opposite here. So one line is going to be very flat this way, and one line is going to be very steep this way. So if you're going to go put these in to your calculator or whatever it might be, or just plot these on your own, you'll see that as well. But if you want, let's do it together real quick. All right. Whoops. The wrong way by accident. So in this case, if we have these problems right here, and you can't see what I'm doing, so let's make sure you guys can see it. So turn this over and let's just sketch this real quick. So I'm going to have the point 20, 0 and 20 here, and then we'll have the point 15 and 15 here. Sorry, it feels like you're on a boat. My kitchen table is not as steady as you might think. So we'll have this right here and this line right here. And hold on a second, I'm gonna get another colored marker so that way I can get this Oops. Okay, sorry about that. I paused the recording and hopefully we can get, I got colors now here. So let's just say P equals X plus 10Y. Okay, that's our green line. So let's just rewrite this as a Y equals MX plus B form, okay? So that means I move X to the other side, X becomes negative, and then I divide both sides by 10. And then I have B plus P divided by 10, which let's just think about plotting this line right here, Y equals negative X divided by 10, which means the slope is negative 1/10. Rise over run, which would mean a value of 1, and maybe say 10 is here. So you'd have these green lines like this going out for the green profit one. And in this case, it should be a no-brainer. Profit maximizing point is 0 and 20 because that means you'd produce 0x plus 10 times 20y, which will give us 200. Whereas if you were to do, say, 15 plus 10 times 15, right? So 1 times 15 at the other corner point right here, you're only going to get basically 165. So that's not, again, that's not a, oops, sorry, you can't see that. 200 and 165. Now let's use blue. I'm sorry if the green doesn't show up as well as it should. I'll try to pick a different color next time, but I think you saw what I was doing. The other one that I have is blue, and we'll have, which looks like black as well, but follow with this. We have 10x plus y. In this case, you guys probably think the line probably goes this way and then comes through 24. Let's just verify that. So we move y to the other side, or move x to the other side. We'll have negative 10x plus p, and we'll just disregard the p and just focus on this. So that means the slope is negative 10, which means basically a drop of 10 and a run of 1, which means if we were to go over 1 unit and up 10, it would look, oops, sorry, other way around. 1 unit, 10 units down and 1 over. So it would look something like this. Again, feel free to sketch this on your own. Pause the video if you want to double check to make sure. But basically, you're moving out this way with the profit values, and you'd see that basically 24 and 0 is your profit maximizing for this profit function. It would make sense too, right? You want to produce more X units because you get $10 versus $1 for every Y unit. It seems obvious that way. Maybe not obvious yet. Maybe now you're starting to think, oh yeah, that's, I would rather sell something that I make $10 on than $1, right? Okay. All right, so linear programming is basically concerned with finding the optimal value. We've kind of already been doing it. You might see the objective expressed as Z in some textbooks. So Z equals AX plus BY, where A is maybe the coefficient that you'd be earning or the value you might earn from selling a number of X units or producing X units or whatever it might be, and also the same for Y similarly. Now, you also have to have your non-negativity constraints in there because you're not going to have negative variables. In other words, you're not going to produce negative boats, negative quantities of any good, right? You're not going to produce negative calculators or negative Xboxes or negative gallons of milk. It's always going to be positive units, okay? The optimal solution is basically the values or set of values that optimize the objective function. So, sorry, I went the wrong way. So first is the fundamental theorem of linear programming. Basically, if the optimal value of the objective function in a linear programming problem exists, then that value must occur at one or more of the corner points of the feasible solution. So right now, if I was to go back to make you guys think about this, right? All we're saying is that it must occur at one of these corner points, right? Or along maybe that line. What if that profit value line had been this exact, say, line right here? Then any value between here and here would be profit maximizing, any allocation between it, if that profit function followed that line. So you might have a problem like that in the future. Be aware of that. And theorem 2 is the existence of an optimal solution, right? So if the feasible region for a linear programming problem is bounded, in other words, it's a bounded set like this. This is a bounded set right here, right? All the values are, you can put in a circle, it makes sense. Then both a maximum and a minimum value exist, okay? If the feasible region is unbounded, again, keep in mind, this is bounded up here. Now, an unbounded region might be something like a line like this, and say we're going this way, shading up this and shading up this, which means this is our region. This is unbounded because basically you can't draw a circle on it because this goes out infinitely further away, okay? So a minimum value would exist, right? Because you could either probably figure out it's this value or this value, or a value anywhere along that line. But a maximum value can't exist because basically you can make x infinity, and therefore you can't find it. If the feasible region is empty, so you might be wondering, how is a feasible region empty? Well, that could be if you have constraints that basically say, like, this is one solution set over here, so that's all this, and then this is one of the other linear inequalities and says it's this. Since there's no overlap, there's technically no region that is in the feasible region. So it would be no, it does not exist. So if we want to solve these kind of problems, basically we can set it up as doing the corner point table. And that's kind of what I showed you just a little bit ago. So you can read through this on your own, pause if you'd like. Basically, it's the same exact thing that we've already kind of done. So let's do these problems, but let's use Desmos, okay? So that'll make our lives a little quicker. So again, I'm gonna use technology, make my life a little easier to show you this so the video isn't as long and perhaps you don't get quite maybe as bored. Maybe you guys are really riveted. This is pretty cool stuff, I think. It's kind of neat maybe to see how these objective functions factor in. So here's what I'm gonna make this down here, and then I'll put it back up there. So let's put in that maximizing, or that profit maximizing function. So we have basically z can be any value we want. So let's put it as, well, let's just put in our constraints first. So we have 2x plus y is less than or equal to 20. That's one of our curves. Then we have 10x plus y is greater than or equal to 36. And then we have 2x plus 5y is greater than or equal to 36. And again, we have x greater than or equal to 0 and y greater than or equal to 0 as well. Well, that's a lot of color, isn't it? Oops, it disappeared. Bring it back. So if we're looking at this, we want to figure out which regions are shaded the most. And in this case, if we look at this curve right here, the red one is this graph right here, and that's saying less than. So that's this line right here. And we're going this way down, so that would be this region is shaded. I think this right here, by the way, is your region that is shaded the most. And I'll show you on the next graph, but basically we could figure out these points by figuring out the two lines that intersect there, and then we can make a matrice with them and have the matrice solve that for us, the system of equations, to figure out those three corner points that we have. And here I'll show you on the next slide, basically those are the points, 2 and 16, 3 and 6, and 8 and 4. So those are our corner points. We put them in, then we put them in our profit function, and we'd have basically 15, 22, and 28. So the maximizing would be 28. The minimizing with the point 3 and 6, creating a value of 15. So if we want to maximize value, it'd be 8 and 4, this one right here. If we want to minimize, it'd be 3 and 6. Okay, let's do the other one. So if we were to put that into our Desmos again, so let's do that real quick. You can see obviously what the answer is, but let's put that in there. And feel free to skip if you want to skip this and you feel really confident that you know how to do this already. So I'll start graphing these. Maybe. There we go. Again, we'll put in our constraints. 6x plus 2y is greater than or equal to 36. Right, that's our first constraint, and then 2x plus 4y is greater than or equal to 32, and y is less than or equal to 20, and x greater than or equal to 0, and y greater than or equal to 0. It's kind of a bummer I don't have you guys to correct me just in case I make errors here, so I gotta make sure I do this all correct, right? So let's zoom out here. We'll figure out which is our region that's shaded the most. it looks like actually this area right here is our shaded region. If you watch my mouse where I'm going, looks like it's just this area right here. And it goes all the way out to infinity. There is no bounds in x, but there is a upper limit for y. Y must be less than or equal to 20. So in this case, this is an unbounded region, which means there is no maximum value, but there is a minimum value. So we need to test the corner points, which would be that point, that point, that point, and that point. So let's go back to our graph and see. So these are our points, right? Move this out of the way. It's probably not visible in yours anyways. But 0 and 20, 0 and 18, 4 and 6, and 16 and 0. And then we plug those into our constraint. And you'd see that there is no maximum value because this goes on infinitely. So how about a feasible region is empty? What does that mean? Well, that means there's no maximum value. So here, let's go back to Desmos for a second because I think it's great to see that. And I'm just gonna delete these out so you guys can see this. And let's say I have, let's use y is less than or equal to 20. And I'm gonna make another one, but I'm gonna say y is greater than or equal to, say, 40. This means there's no overlap in the region, which means there is empty feasible set, which means there is no solution here. Because basically the regions do not overlap in any fashion. It's kind of neat that way. So let's go back here and play from current slide. Now, let's do one application, and this will be the last part of this video, and we should be good. So don't worry, we'll show you here in a second. So in this problem, we have basically a chicken farmer can buy a special food mix, mix A, at 20 cents per pound, and a special food mix, B, at 40 cents per pound. Each pound of mix contains 3,000 units of nutrient N1 and 1,000 units of nutrient N2. Each pound of mix B contains 4,000 units of nutrient N1 and 4,000 units of nutrient N2. If the minimum daily requirement for chicken collectively are 36,000 units of nutrient N1 and 20,000 units of N2, how many pounds of each food mix should be used each day to minimize daily food costs while meeting or exceeding the minimum daily nutrient requirements? So what is the minimum daily cost? So right away, you got to be thinking, oh, we're going to do a minimization problem, and we're minimizing costs. And we need to figure out what our decision variables are. So some of you guys probably already have a great idea of how this is going to work, but just to make sure you guys see this, let's put it together. So we'll go this way. So blue line's not there. All right, so in this case, we need our decision variables. So we have decision variables. So we're probably going to have an X and a Y, right? And in this case, the farmer is choosing how much mix A or mix B he buys. So in other words, the number of pounds of mix A and maybe the number of pounds of mix B. Oh gosh, sorry, the pen got a little sloppy. It's the last page, it's kind of standing upright. But you got this. Number of pounds mix A, number of pounds mix B, okay? So in this case, we know our decision variables. Now we need to do our problem constraints. And so basically he has constraints for nutrient 1 and nutrient 2, right? Nutrient and nutrient. Okay? So we know there's those nutrient constraints, and he is going to have some come from X and some going to come from Y. So let's go back and figure out again. Mix A provides 3,000 units for basically nutrient N1 and 1,000 units for nutrient 2. And then Y, the number of pounds for mix B, well, it's 4,000 X and 4,000 Y. Now, keep in mind, this is really important that you don't mix these up and switch these around. So it might be good for you to draw a table first to do this. Now, we're going to say less than or equal to, right? Or is this actually, they need at minimum the requirements of 36,000 units of nutrient N1 So 36,000 and 20,000. So let's go back a second. Minimum, meaning, for example, if you need a minimum of, say, 8 on a scale of 20 to pass your driving test, if you got a 9, did you pass? You'd probably say, yeah. So in other words, this needs to be greater than or equal to and greater than or equal to. So those are our problem constraints. We also need our non-negativity constraint. Oh boy. Sorry, my handwriting is getting a little. I'm trying to write soft so I don't shake the camera, but when I write soft, it's messy. So x must be greater than or equal to 0, and y is greater than or equal to 0. So, right, greater than or equal to 0, right? Those are basically our constraints that way. Now, the next thing we need to do is figure out our objective function. So we're going to minimize cost. So in this case, C is equal to, right, cost function. So we need to figure out what was the cost again? It was 20 cents per pound. So 0.2 times X plus 40 cents for Y, right? So in other words, you might say C is equal to 0.2 times X plus 0.4 times Y is basically our cost minimizing function. So min cost that, okay? And now all we need to do is put that into a graph and figure out the corner points. So if we do that, let's use our best friend Desmos real quick and plot those in there. So I have 3,000 X plus 4,000 Y is greater than or equal to 36,000. And then I'm going to have 1,000 X plus 4,000 Y greater than or equal to 20,000. By the way, you might be wondering, couldn't I just have written these as like 3x plus 4y is greater than or equal to 36? Yeah, the answer is yes, you could have. You'll see that if I was to go in here and say I put that in 3x plus 4y is greater than or equal to 36, it's the same exact line, right? So you can reduce things down like that to make your life a little simpler if you'd like. I'm actually going to do that so that way it doesn't have such big numbers. So we're going to reduce everything by 1,000, right? We do divide both sides by 1,000, and there you go. So that is basically our graph that we have. And now if you're looking at this, to me, it looks like, we're going to zoom in here. Oh, by the way, we also have which constraints did I not put in there, but I think you guys would already know. X greater than or equal to 0 and Y greater than or equal to 0, right? That makes our graph look really messy, but you guys would see that it's basically, if I was to sketch this out real quick, it's this area right here. So we're going to have this corner point, and this corner point right there. So if we go to our graph and look at this, this looks like 8 and 3. Yeah, I think that's 8 and 3. 8 and 3. And if we look right here, this looks like 20 and 0. And by the way, you shouldn't just say looks. You should probably go calculate this out. But I'm pretty sure these are the numbers, so I wouldn't worry too much. And we have 0 and 9 up here. So if we were going to do corner points, so CP, and we'll do min cost, we'd plug those in. So 0 and 9, and 8 and 3, and 20 and 0. So let's just put those in our calculator, verify that we get the same answer. And again, we'd be putting them in here. And so 0 times 0.2, 0.2 times 0 plus 0.4 times 9. I got 3.6. And oops, move that over here just a little bit. And then I have 8 times 0.2 plus 3 times 0.4 We get 2.8. And then we have 0.2 times 20, and we get 4. So it looks like our cost minimizing value is that value right there. So there you go. Simple as that. And that's basically 5.3, where the things that you want to remember is you want to do your decision variables, your problem constraints, non-negativity constraints, and your objective function. And then do corner points and basically sketch it out. Always sketch these things out. You'll be so much happier you did. Okay, and the other thing is make sure your decision variables make sense. Like if you're talking about cost minimizing the number of mix pounds you buy, then these variables up here should be the same. So we'll skip that. And that's it for 5.3. So that's all of 5.3. Let me know if you have questions, like always. Okay.